So the next thing we're going to talk about is the GCD, greatest common divisor, least common multiple. So let A and B be integers such that A and B are not both 0. The greatest common divisor of A and B is the largest integer D such that D divides A and D divides B. And the notation we use for this is GCD AB. So in other words, to kind of write this succinctly, GCD of A and B is the maximum element of the set D such that D divides A and D divides B. If I write max before a set, what I mean is the maximum element of that set. So for example, what's the GCD of, I don't know, 2 and 4? Yeah. 4. Well, almost. It's going to be 2 because, so, right, so we might be sort of forgetting this notation, but, right, so this means that D, so D goes, we're trying to find the biggest number that goes evenly, like, you know, into, which divides A with no remainder and divides B with no remainder. So, so 2 goes into 2 with no remainder, 2 goes into 4 with no remainder, but 4 doesn't go into 2 with no remainder, right? Because, okay, how about the GCD of 4 and 6? Any other? Yeah, right. Because, I mean, if you kind of think of this, what are the divisors of 4? The things that go into 4 are 1, 2, and 4. The things that go, you know, evenly into 6 are 1, 2, 3, and 6, right? And this is like, so these are the divisors of 4, and these are the divisors of 6. We're taking the greatest common divisor. So you're taking the biggest number, which is a divisor of both of them. And that's 2. So your only options here are like the number 1 or the number 2, and 2 is bigger than 1, so you take the biggest one. How about 7 and 13?
1.
Right. How come?
Because both are prime.
Exactly, yeah. So both are prime, so like the only divisors of 7 are 1 and 7. The only divisors of 13 are 1 and 13. The only common divisor is 1. Well, okay, what if I take so I'm going to write these numbers kind of weirdly, but it's going to illustrate something. So suppose I take 2 cubed times 3 squared times 7. So I'm asking for the GCD of this number, which I don't even know what it is, but it's not going to matter much. 2 squared times, let's say, 7 cubed. Okay, 7 is definitely a divisor, right? 7 goes into both of them because you can see it in the prime factorization. But you can actually do better. 2 definitely goes into, I mean, both of these are good answers because they both divide it, but yeah. Oh, sorry. That looks good, yeah, because is that what your answer was as well? 2 squared times? Yeah, so so okay, all of these answers they're all divisors, but indeed, 2 squared times 7 is going to be the best answer here because it's the biggest one, right? So yeah, 7 goes into both of these things, 2 goes into both of these things. Actually, 2 squared goes into both of these things, but in fact, 2 squared times 7, evenly divides both of these things. And actually, this is a kind of general principle that we can always apply. So if you know the prime factorization, what you can do is just go through each prime and look at the exponent and take the smallest exponent, like out of these two options, right? So, this one has 2 with an exponent of 3. That one has 2 with an exponent of 2. 2 is the smaller number. This one has 3 with an exponent of 2. This one, you can think of it as being 3 with an exponent of 0, right? You can think of this number as 2 squared times 3 to the 0 times 7 cubed. So we're going to put 3 with exponent 0 here. And you can see 7 with exponent 1 or 3. 1 is smaller. So, and this is always going to give you a divisor because, this is always, whatever number you get from this process will divide both of them. And it's going to be the greatest common divisor. And that's because of the unique prime factorization of these numbers. So you couldn't pull out a different prime. Like, for example, this number is not divisible by 5 because 5 is not in the prime decomposition. Okay, so let me tell you now about the least common multiple, which is almost the same thing. And then I'll come back to that prime factorization thing that I was talking about there. So let A and B, so this time I'm going to make them both non-zero integers. The least common multiple of A and B is the smallest positive integer m such that A divides m and B divides m. And our notation for this is LCM AB. Okay, so in other words, the LCM of A and B is the minimum positive integer such that A divides m and B divides m. Okay, so it's kind of like, these things are kind of related, right? But here I'm taking the biggest number that kind of goes into A and B, right, or with no remainder. So the biggest thing that divides both of them. Here I'm taking the smallest thing that they both divide. So let's do a few examples to get used to it. So if I take LCM of 2 and 4, now your answer becomes correct. So, right, that's going to be 4 because 4 is a multiple of 2 and 4 is a multiple of 4, and there's no smaller number that's a multiple of 2 and 4, right? This is the smallest possible number, which is a multiple of 2 and 4. For example, so if we do, what's this one? Sorry?
12.
Yeah, exactly. So again, you can kind of think of this as taking, looking at all the multiples of 4. So the multiples of 4 are 0, 4, 8, 12, 16, 20, ... The multiples of 6 are 0, 6, 12, 18, 24, etc. We want to take a common multiple, so we want to take something which is in both lists, which is as small as possible. So if you look, these are not common multiples. They're not multiples of 6. these are not multiples of, well, okay, sorry. I want to avoid 0. Yeah, you don't, otherwise 0 will always be the least common multiple, because, yeah. So that's why I guess here I said it's the smallest positive integer m such that they both divide it. So anyway, the answer is 12. What if I take, oh dear, what? I have to actually think of what the answer is. Yeah, 7 times 13, whatever that happens to be, which I guess is 91, I think. But right, because if you think about the multiples of 7, so this is a game because these things are prime. So you're not going to see a multiple of 13 until you take 7 times 13. Any questions about these examples? Okay, let's do another one of these ones involving the prime factorization. So what's the least common multiple of these two numbers? Sorry? 4. So, well, 4 is probably not going to be a multiple of this number because this is a pretty big number, right? So it needs to be, it's a number which is like some multiple of this and also some multiple of this. So it's got to be, in particular, it's got to be bigger than these two numbers. Yeah, exactly. How do we know that? So if you have a number m, which is a multiple of this number, like the first number, if I think about the prime factorization of m, so let's say m is a multiple of 2 to the 4, 5 squared times 7. The prime factorization of m has to include 2 to the 4, it has to include 5, and it has to include 7, because any multiple of this number will be divisible by those primes. So the prime factorization of m, so the factorization of m must include 2 to the 4, 5 to the 1, so at least, kind of at least, 5 squared and 7. But also, if it's a multiple of this number, the prime factorization has to include 2 to the 1, 5 to the 3, 11 to the 1. So if it's also a multiple of the second number, it has to have like 5 with an exponent of 3. So the first bit of information is redundant, kind of. So it has to have at least like 2 to the exponent 1. But we already know it has 2 to the 4, so that covers that. It has to have some like 5 cubed, and it has to have 11. So basically you go through the numbers and you take the biggest exponent, right? So 4 is bigger than 1, we take 4. 3 is bigger than 2, we take 3. I've got 7 to the 1 here, 7 to the 0 here. I've got 11 to the 1 here, 11 to the 0 there. So it's got to be this number. Yeah, so there's always going to be a lowest common multiple and greatest common divisor because, there exists, so if I take, for example, a times b, that's a multiple of a and it's a multiple of b. So there exists at least something which is a multiple of a and b, and you can always take the smallest one. As long as there exists one of them, you can always take the smallest one. So yeah, there always will be a smallest one. Yeah, 1 divides both of them, so therefore there's something that divides them, so therefore there's a biggest one. Okay, so let me kind of, without proof, I'll give you the kind of principle that I'm trying to lead you to here with these examples. So the kind of thing I'm trying to show you here is, so suppose that a is a number of the form p1 e to the 1, e1, p2 to the e2, pk to the ek, and b is p1 to the, let's say, f1, p2 to the f2, pk to the fk, where p1, p2, up to pk are distinct primes, and all of our numbers e1 up to ek and f1, f2 up to fk are non-negative integers. So non-negative just means at least 0, right? Then the GCD of A and B, well, to get the GCD, if we apply the same kind of principles we were thinking about before, what you're going to do is you take each prime and you look at the exponent in A and the exponent in B, and you take the smallest one. You look at the second prime, you look at the exponent in A and B, and you take the smallest one. So notationally, this is P1 to the minimum of E1, F1, P2 to the minimum of E2 or F2, dot, 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 up to Pk to the minimum of Ek or Fk. Okay. Which I understand notationally this looks kind of weird, but the kind of principle is exactly what we were doing. So you kind of write each of these things as a product of primes, and for each prime you take the smaller exponent. Now that will always be a divisor of A and B, and because of the prime or the fundamental theorem of arithmetic, so the unique prime factorization, this is going to be the only, or sorry, this is going to be the maximum, the greatest common divisor. You couldn't have a bigger divisor than this. Okay, and similarly, the least common multiple of A and B, so this is kind of continuing on from there, is going to be P1 to the maximum of E1 or F1, P2 to the max E2, F2, multiplied product, dot, 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 Pk to the max of Ek, Fk. So a kind of weird consequence of this is that if I take the GCD of A and B and multiply it by the LCM of A and B, can anyone, well, I know probably we're kind of stuck on not, yep, A times B, exactly, yeah. Because if you think about what this does, imagine, the LCM is this, and the GCD is this. When I multiply this number, which I understand is a horrendous kind of notation, but there's not really any better notation for this. But if I take this number and I multiply it by this number, you can collect up all the P1s, like all the factors of P1, and collect up the factors of P2, and so on. And you'll get P1 to the power of the minimum of E1 and F1 plus the maximum of E1 and F1. If I take two numbers and I take the minimum of the two numbers and the maximum, and I add them together, that's the same as just adding the two numbers. If I take the minimum of, let's say, 3 and 5 plus the maximum of 3 and 5, well, I mean, that's just clearly 3 plus 5, right? So if you think about it, what this is going to give you is the same thing as you get by multiplying A and B, because the exponent on P1 will be E1 plus F1 when you multiply A and B, but it's also going to be E1 plus F1 when I multiply the GCD and the LCM. Okay. So in some convoluted way, this actually implies this, which can be sort of useful because suppose somebody tells you to compute the GCD and the LCM of two numbers, and let's say you compute the GCD, then you're pretty much done because you don't have to go through some complicated procedure to get the least common multiple because you can just divide. You can just take, once you know this information, once you know the GCD, you just take A times B divided by that number, and it gives you the LCM. So kind of, it's a lot, once you know one of these things, it's easy to get the other one, right? So like I said, once you know one of these things, it's easy to figure out the other one. But that kind of begs the question, how do I even figure out what one of these things are, right? How do I compute the GCD, for example? Or how do I compute the LCM, whichever one's easier? I mean, so we're going to focus on computing the GCD. But what's like a good procedure for doing that? So, okay, we sort of already have one procedure for doing it, right? If you really wanted to, what you could do is take the prime factorization of A, which, okay, it's not that easy to find the prime factorization, but you could just do some trial and error to try to get the prime factorization of A, get the prime factorization of B, and then you could write, you could just take the minimum exponent and you could write that down, right? It turns out that that's not a very good approach. Actually, if you know anything about, like, I don't know, cryptography or internet security, these kinds of things, actually, a lot of like banking systems, like security for these kinds of things, are based on the principle that if I have a really big number, that we don't have any good way of finding the prime factorization. Like nobody knows of a good efficient method. If I give you a huge number and say find the prime factorization, it's a hard thing to do. And so basically what I'm saying is, if you found a really good way to find prime factorizations, like in a really quick method, you could probably hack into a lot of online banks and things like that, steal a lot of money. So probably an approach which is like based on factoring into primes, it's probably not going to be the smartest approach because, like I said, if we had a good method to do that, we'd be rich. Well, if you wanted to use it for evil. Does that make sense? So what I'm saying is, if you're trying to find the GCD, yes, you could do the prime factorization, but I wouldn't recommend that method. So what I want to do now is tell you about another method for doing it, which is something called the Euclidean algorithm. So this is going to be basically the whole point of this is that this is a method for computing the GCD of A and B without needing to find the prime factorizations of A and B. So imagine somebody gives you two numbers and they want you to find the prime factorization. We're not going to find the prime factorization, but we are going to find the GCD. So yeah, so suppose someone gives you, so suppose you want to compute, so A and B are let's say, positive integers. Let's say A is at least as big as B, and you want to get the GCD. Okay, so right away I don't know how to do that. But one thing I do know how to do from earlier is I know how to find the quotient and the remainder if I divide A by B. Okay, it's not clear in any way why that's useful, but it will be hopefully clear later. So step one is going to be find the quotient and remainder when the bigger number, so it kind of matters which one of these is bigger, right? So we always want to take the bigger number and divide it by the smaller number. So when A is divided by b. So the quotient is going to be q, and the remainder is r. So we remember how to do this, right? If I want to get the quotient, I take a over b and round it down, right? And then you can get the remainder by kind of subtracting, taking a minus b times q. Do we remember this division theorem? So if I write a as a multiple of of b plus some remainder, what do I know about the remainder? So this was now it feels like a while ago, but last week, or maybe it was Monday. I can't remember. Yep. Well, it's definitely less than a, but it's actually going to be. In fact, it's even less than b. So, but that's kind of the point, that the remainder is not very big. So the reason is, if r was bigger than b, then we could, we would have a remainder bigger than b. We could kind of pull out another b from a, right? And you'd get a smaller, you'd get a bigger quotient. So here's the magical thing, which makes the Euclidean algorithm work. The GCD of a and b is going to be equal to the GCD of b and r. Okay, so I'll prove that to you, but for now I'll just kind of say, so this is a magical thing. I mean, this is super useful because, so imagine a and b are big numbers, and what we've done is we've said, okay, I can compute the quotient and remainder. That's something which is pretty easy, right? You just kind of, it's pretty easy to compute the quotient and remainder. And then I can just say, the GCD of a and b is the same as the GCD of b and r, where I know that r is smaller than b. So I've basically taken my problem with two big numbers, and I've reduced it to a problem involving smaller numbers, okay? And then you can repeat this. You can say, okay, let's take the quotient of b when you divide by r, and the remainder, and you can reduce it again to two smaller numbers. And then you can repeat that and keep repeating it, repeating it, and eventually you get down to some numbers which are so small that you just know the answer. It's just an easy calculation. Okay, so that's the sort of principle here. The point is, if you write with a as b, if you kind of do this quotient remainder thing, it maintains the GCD, and that allows you to reduce your big numbers down to small numbers, where you can just compute it directly. So let's prove that this is true. Okay, so what I want to prove is that this kind of magical thing is true. So this is a slightly different version of proposition 5.12.1 in the notes. But okay, what I'm going to write is basically the same as what it says. So let a and b be integers such that a and b are not both 0, and suppose q and r are integers such that a is equal to bq plus r, then for any integer d, so I'm going to write this, maybe I'll write this with kind of logical notation. So d divides a and d divides b if and only if d divides b and d divides r. In other words, what this says is that if I look at the common divisors of of a and b, so these are the numbers that divide both of them, that's exactly the same as the set of common divisors of b and r. So in particular, if all the common divisors of a and b are the same as all the common divisors of b and r, so in particular, the biggest common divisor of a and b is the same as the biggest common divisor of d and r. So GCD of AB equals the GCD of B and R. So before I prove this, are there any questions about the statement? So this sounds like maybe a weird statement, but the proof is actually really easy. So we're proving an if and only if statement, right? So we need to prove both directions. So let's prove, oh, it doesn't really matter which one comes first, but let's prove this direction, right? So that we want to prove this statement implies this statement. So suppose that D divides A and D divides B. So what do we want to, so this is what I'm assuming. And what do we want to prove? So I assume that this side is true, and I want to prove that this side is true, right? So my whole goal right now is to prove that D divides B and D divides R. Which of these is easier at this point, given my assumption? So I'm assuming D divides A and B, and I want to show that it divides B and R. So I want to show two different things. Which one's easier? Yeah, exactly, yeah. It is like that simple, right? So, I mean, I'm already saying D divides B, so, I mean, that's, you know, just by assumption, right? I mean, D divides B. Okay. The more interesting part is proving that it divides R, right? So also, so I can rewrite. So now I'm trying to prove it that D divides R, and I can rewrite R using my equation. So R is equal to B times Q minus, or sorry, A minus B times Q. So why am I happy at this point? Yeah, totally. So, you know, yeah, D divides A, D divides B, so therefore D divides B times Q. So I've got two numbers that are divisible by D, and I'm subtracting them. If you have two numbers divisible by D and you subtract them, it's a number that's also divisible by D, right? In other words, I can factor out a D from here, I can factor out a D from here, so I could factor out a D from everything. So since A divides B, or sorry, D divides, sorry, A and D divides B, we know that D divides A minus BQ. Okay, actually there was a proposition we proved which would imply this. So remember, if we have something divides A and something divides B, then it divides X times A plus B times Y for any X and Y. So, I mean, that's kind of what we're using here. So D divides R because R is equal to A minus BQ. Okay, now for the other direction, it's similar. So assume D divides B and D divides R. Okay, well, then obviously D divides B because we're assuming it divides B. And now we can write, so A is equal to BQ plus R. So since D divides B and D divides R, D divides, well, it divides A because it divides B times Q plus R, so, and A is equal to B times Q plus R, so it divides A. Okay. So we will continue. So I'll maybe do a quick example of how you can use this Euclidean algorithm, but we'll start on Monday with doing some more examples because, yeah, this is it's a cool trick, and it's also important for you to know how to use it. So let me show you how this Euclidean algorithm works in practice. So suppose I'm asking you to compute the GCD of 765 and 1428. So I start by, I take my big number, which is 1428, and I compute the quotient and remainder with 765. Which, okay, you might need a calculator for this, right? So in the future, yeah, I mean, you might need to bring a calculator for these sorts of things. But if you do the computation, you'll see that the quotient is 1 with a remainder of 663. So this proposition we just proved, so if I think of, my 1 is Q, and this is R, and this is A, and that's B. What we just proved says that the GCD of this number and this number, 1428 and 765, is equal to the GCD of 765 and 663. So that basically has reduced our numbers to something a bit smaller. Of course, I wouldn't call these small numbers, right? They're still kind of big. But it's made our situation a little bit better. So now what I do in the algorithm, I take my number from here, 765, I slide it over. I take the 663, slide it over. So we want to compute the quotient and the remainder. I think this time the quotient's pretty clearly equal to 1, and the remainder is 102. So now we can use our proposition again to get that this is the GCD of 663 and 102. Slide it over. Okay. What's my, so if I'm taking 663 divided by 102, what's the quotient? Yeah. So now we can start seeing these things without even using a calculator, right? We could just see, I mean, this is definitely going to go in 6 times. So that would make 612. So left over, I've got 51. Yeah, thanks. And now we slide this over. Oh, so yeah. So what we can say now is that this is equal to the GCD of 102 and 51. Which actually, well, can anyone see what this is already? The biggest thing that divides 102 and 51 is actually 51. 51 divides both of them, right? But even if we didn't notice that, that's okay. We can keep going in our algorithm. So we compute the quotient. The quotient is 2. The remainder is 0. I can write this as GCD of 51 and 0. And if you have the GCD of anything with 0, it's just equal to the thing. So the biggest thing that divides, that goes evenly into 51 and 0 is 51. Okay, so basically, you do this thing until your remainder is 0, and then your answer is always the number you wrote here at the last step. Okay. Let me give you another example using this Euclidean algorithm. So we talked about this last time, but let me show you again how it works. So suppose you were asked to compute the GCD, or in other words, the greatest common divisor of 1830 and 4697. So the first step is take your bigger number, 4697, and find the quotient and remainder when you divide by 1830. Which, okay, we can kind of tell 1830 goes in twice here because it's, if you double 1830, you get about 3660 or whatever. But you can also use a calculator if you want, as long as it's one of the standard UVic calculators from the bookstore. So if you feel like you are going to need a calculator for this, then you probably want to get the one that you can use on tests. Okay, so we find the quotient is 2, the remainder is 1037. 1037, is that right? Yeah, I think that's right. So the way the algorithm works is now I kind of slide this over, and I slide this over. Okay. And again, we try to find the quotient and the remainder. This time, the quotient is just 1. 1037 goes in once. And then what's left over is, what is it, 793. Okay. And you just keep doing this until, until you get down to something you can deal with. Or actually, really, you keep doing this until the remainder is 0. So 1037, you can write as 1 times 793 plus 244. So next, we take 793, which is something times 244, plus some remainder. This time I think it's 3 is the quotient. The remainder is 61. Then we have 244. If you think about it, this is actually exactly 4 times 61. Plus 0. So what's the GCD? Yeah. Exactly. So basically, you keep doing this until you get a remainder of 0, and then you can just kind of lock this in and say, oh, the answer is 61. Okay. So last time we looked at the actual reason for that, the proof. So the proof of that, this is basically based on the fact that the GCD of these two numbers is always equal to the GCD of these two numbers. And then the GCD of these ones is equal to the GCD of those ones, and so on and so forth, until you get down to the GCD of 61 and 0, which is just 61. So to kind of explain why this works, so this is using some proposition from last time. So if I take 46, 97, and 1830, that's equal to the GCD of 1830 and 1037, which is the GCD of 1037 and 793, which is equal to the GCD of 793 and 244, which is equal to the GCD. Okay, you don't have to write all this every time, but this is why it works. And then the GCD of 61 and 0 is just 61. So here's a question. So, which maybe doesn't seem that related to the GCD yet, but it will in a second. So my question is, which integers can be written as in the form, 4x plus 6y for some integers x and y. So this is kind of like that thing about, remember when we were doing induction, I think we had an example like which integers can be written as a sum of 3s and 5s or something. This is kind of similar, except a little bit different, because now I'm allowing x and y to be positive or negative. So that you don't have to use positive numbers, you can use negative numbers or whatever. But the question is just, which numbers can you represent as 4x plus 6y for some x and y? It might be easier to ask first, or to think first, what numbers can you not represent? So does anyone have an example of a number you probably can't get in this way? Yeah, exactly, totally, perfect. That's what I'm looking for. So you can't get any odd numbers. The reason is because, because 4 is divisible by 2, so 2 divides 4, and 2 divides 6. So we had some proposition from earlier which says if something divides some number and something divides another number, then it divides any kind of combination of those numbers multiplied by integers. So 2 will always divide 4x plus 6y for all integers x and y. So in other words, since these things are even, 4 is even and 6 is even, any kind of combination like 4x plus 6y will always be even. So you can't make any odd numbers. But then you could also ask, can I make all the even numbers? And the answer is yes, because, well, let's try to make the smallest even number except for 0. Okay, like the kind of simplest even number, which is 2. Well, we can make that by taking, let's say, if we take 6 times 2, or sorry, 4 times 2, minus 6 times 1. Or in other words, plus 6 times negative 1. So this is, I'm taking x is equal to 2, y equals negative 1. Right? And that's going to give me 2. So this shows that I can make the number 2. But then if you think about it, if I can make the number 2 from a combination of 4s and 6s, then I can make any even number, right? Because any even number is 2 times k for some k. So if I just multiply both sides by k, so to make a number 2k, I just take 4 times 2k, or maybe I'll do this in more than one step. So if I take 4 times 2 plus 6 times negative 1 times k, that's going to be 2k for any where k is an integer. But then if I bring in this k, that means that 4 times 2k plus 6 times negative k is 2k. And so in other words, we can make any even number. Okay, this is just one example, but it turns out this is part of a more general principle. So the special thing about the number 2 here is that 2 is the GCD of 4 and 6. So this is a general fact that so let a and b be integers which are not both 0. So for any integer d, there exists x, y in the integers such that ax plus by is d if and only if the GCD of a and b divides d. So with the example here, the GCD was 2, and we showed that we could make any even number, right? So if the GCD of 2 numbers is, let's say, 3, then we want to show, okay, we can make every multiple of 3. Or if the GCD is, 57, then you want to show you can make every. So what this says is that you can make any multiple of 57 by taking a combination of of the form ax plus by. Okay. So I'm not going to formally prove this, but let's look at an example of how you would do this in practice. So the trick is, for doing this, if I gave you some a and b, and I ask you to represent some number as ax plus by, the trick is, well, to show that we can find x and y such that ax plus by is equal to the GCD by kind of going through doing the Euclidean algorithm and then sort of going backwards. So by computing the GCD using the Euclidean algorithm, and then sort of going backwards to get our x and y. Okay, this is very vague, but it'll hopefully be clearer if I give you an example. And then, but here's the thing. So the key thing is to show that you can make ax plus by equal to the GCD. And then if you can do that, then you can, of course, do any multiple of the GCD by just multiplying both sides by k. So just like we did here, the key thing was to show that I can make 2, the number 2, from like 4x plus 6y. And once we've made 2, we can get any even number by just multiplying everything by, some integer k. Okay, let's see an example. So this whole thing was trying to compute the GCD of 46, 97, and 1830. And we determined that it's equal to 61. Okay. So using this calculation, let's see how I can represent the number 61 as a multiple of 4697 and a multiple of 1830. So we want to find x and y such that 4697 x plus 1830 y is equal to 61. So the procedure is, so if you were just given this and asked to find x and y, okay, what I would do is first do this calculation. So do the Euclidean algorithm to find the GCD, right? And now, like I said before, we want to get the x and y, we want to kind of take this calculation and sort of do something backwards. So so what I'm going to do is I'm going to start on the second last line of the calculation, where I've got a 61 as the remainder. Right? So the last line of the calculation has a 61 here, but I kind of want to start here. And if I start here, I can kind of solve for 61. So we get that 61 is equal to 793 minus 3 times 244. So this is from, so let's say I number these lines 1, 2, 3, 4, 5. So that comes from line 4. So now what I do is I look at my smallest number. So okay, I don't mean 3. So 3 is a small number, but I mean out of the two kind of things I was using in the calculation, I take the smallest one, and I look back at my calculation at line 3, and I can see that you can rewrite 244 in terms of these other numbers, which in some sense, we're going to keep replacing the smallest number that we have in our calculation with bigger numbers. And eventually, at the end, we're going to get something in terms of these two numbers at the top, which is what we wanted. So I'm going to replace this 244 with 1037 minus 1 times 793. So this is from line 3. Is it clear how I got that? Just took this thing and solved for the 244 by pulling that to the other side. So now, okay, one thing I don't want to do is like multiply things out. So I mean, we're going to kind of treat these numbers in here as sort of variables, right? And kind of move things around. So this is going to be -3 times 1037 plus 4 times 793. Because I've got one 793 here, I've got negative 3 times negative 1, which is 3, so 3 more 793s. Right? And now we look at our next line, or going backwards in the calculation, we look at our next line, and we see, my 793 can be rewritten in terms of these two numbers. So I do it. So this is negative 3 times 1037 plus 4 times 1830 minus 1 times 1037. Okay, so maybe I'll write that as 4 times 1830. So I've got a negative 3, 1037, and then I've got minus 4 more. So I've got minus 7, 1037. Okay, so maybe I'll finish this here. So now I see I've got, I look at my last line of the calculation. I've got something in terms of, I can solve for 1037 and plug it in here. So we finally get 4 times 1830 minus 7 times, so 1037 is 4697 minus 2 times 1830, 4697 minus 2 times, oops. So that's going to give me negative 7, 4697 plus actually 1830s. Did I get this right at the end? Oh, maybe I didn't even write it down, but oh yeah, no, so I got that. Yeah, right. So this is going to be equal to 61, right? That's where we started. So 61 equals, and then it's equal to this. So, right, so we get that x is equal to negative 7 and y is equal to 18, right? Because, right, we've got a negative 7 here, 18 there. Any questions about that? So basically, if you can do this Euclidean algorithm, you can also find these x's and y's. By the way, so I mean, what if this asked you to find like x and y such that this equals 122? Well, what you could do is find the x and y such that you get 61, and then you multiply them by 2, right? So if I wanted to make 122 here, which is 2 times 61, what I would do is find this x and y, and then just take like negative 14 and 36 instead, because that's going to work. Okay, any questions about that? Okay. All right, so let's talk about the special case where two numbers have GCD equal to 1. So definition, so let a and b be integers. We say that a and b are relatively prime if they have a GCD, if they have GCD equal to 1. So in other words, well, maybe let's do some examples. So for example, if I take like you know, A is 12, B is 35. You know, if you think about it, the GCD of 12 and 35, you know, the only positive integer that goes evenly, that divides evenly into 12 and also divides into 35 is 1, right? Now, if you think about it, like, I mean, why? Why is that the case? And the reason is, if you think about the prime decomposition, right? If I have 12, 12 is 2 squared times 3. That's the prime decomposition of 12. If I have 35, it's equal to 5 times 7. And the sort of point is that there's no primes in common. No. Right? So if there was a prime in common, then you know, that would divide both of these numbers, and the GCD would be bigger than 1. And if you look at the prime decompositions and there's no primes in common, then that means that the GCD must be 1, because nothing divides both of these numbers. Basically, if you had an integer that divides both of these numbers, you could say, what is the prime decomposition of that integer? It would have to have some primes in common here and also here, but that can't be the case. Yep. So I should say, like, so there's no such thing as saying like a number is relatively prime or is a relatively prime, right? So really this is a property of two numbers. So two numbers are relatively prime to one another if this happens. So I mean, generally, if I have some integer a, there's going to be infinitely many b which are relatively prime to it. Yeah, because there's infinitely many primes. So for example, like if I take 2 primes, for example, like 13 and 29, that's a prime, right? Feels prime, doesn't it? That's going to be 1, right? So 2 different primes, that's one example of 2 things that are relatively prime. Okay, but generally speaking, like if you write the prime decomposition and they have nothing in common, then that means that they're relatively prime. But yeah, it's good to remember that this is a property of 2 integers, not 1 integer, right? So it's, yeah. Any questions about that? Okay, so using this thing that we've just done about representing numbers as ax plus by, so a and b are relatively prime if and only if there exist integers x and y such that ax plus by is equal to 1. Okay, this is just a special case of what we were doing before. So before we were saying, you know, if I've got any 2 integers, I can write them as ax plus by equals the GCD. Well, here we're talking about relatively prime, so that just means the GCD is equal to 1. So if they're relatively prime, then there exist these integers making this equal 1. And of course, if there exists x and y making, you know, where this sum is 1, they have to be relatively prime. Because if a and b had a prime or some divisor bigger than 1, so that would be a number that divides ax and a number that divides by, but then it would be a number bigger than 1 that divides 1, but that can't happen, right? So if you ever are given, you know, integers and you know that they're relatively prime, you know that there exists x and y such that this is true. And this is a very useful thing. So okay, let's use this in a proposition. So what is it? 5.14.4. So for any integer a, so the integers a and a plus 1 are relatively prime. Okay. So yeah, so what this is saying, right, if I take two consecutive integers, they're always relatively prime. So they can't have any common divisors except for one, the number 1. So to do this, I want to use this fact here, because it turns out it's pretty easy to find my x and y in this case. So I'm just going to let x be -1 and y equals 1. So then ax plus a plus 1y is -a plus a plus 1. The a and -a cancel, so that gives me 1. So therefore, a and a plus 1 are relatively prime. Okay. So notice, like so I didn't really say anything about what the, I mean, in some sense, I didn't really do anything about the GCD or anything here. I mean, I just used this fact. So it's kind of a powerful thing, that this thing. So it's quite useful. So all I have to do is find two numbers such that when I multiply them to my original numbers, I get 1, and add. So multiply them and add them up. In this case, yeah, you just take -1 and 1, and it's going to work, right? Because, yeah. Any questions about that? Okay. So that's a fairly simple application. Let's look at something more interesting. So this is proposition. Oh, sorry, I labeled this one wrong. This should have been 5.14.1, but anyway. So now we're doing 5.14.4. So let a, b, and c be integers. So what I want to prove that is if a divides b times c, and a and b are relatively prime, so GCD a, b is 1, then actually a divides c. Okay. So intuitively, maybe, if you're used to this, if you've kind of internalized these ideas about prime factorizations and things like that, this should be kind of clear. I mean, in some sense, we're saying here that, if you think of the prime factorization of a, for example. So to say that a divides b and b times c, that means that all the primes here appear in the prime decomposition of b and c, or b times c. But the fact that a and b have GCD 1 tells you that none of those primes appear in the prime decomposition of b. But if they appear in the prime decomposition of the product, but they don't appear in b, they must all appear in c. And so you must have that a divides c. But let's do this. So OK, we could do it by arguing using the prime decomposition like that. But let's do this using this, this thing we've built up about the ax plus by thing. So since the a and b are relatively prime, so since we know that there exists x and y such that ax plus by is 1. which maybe doesn't seem that useful. What does this have to do with A dividing C or A dividing BC? I mean, there's no clear connection yet. But the trick is to take this equation and multiply both sides by C. And then something kind of nice happens. So if we multiply both sides by C, we get AX plus BY times C is equal to C. If I kind of bring that through, we get ACX plus BCY is equal to C. Well, okay, it's maybe still not that clear, but so I want to show that A divides C, and I've kind of got this equation for C. So C is equal to this. So what I can do is show that if I can show that A divides this side, well, this is equal to C, so then A will divide C. So let's show that A divides this stuff. And to do that, I want to show that A divides the first part, so ACX, and it divides the second part. The first part's really easy, right? I mean, A divides A times C times X because this has an A right in it. So clearly, A divides A times C times X because there's an A right there. But also, so why, can anyone tell me why A divides B times C times Y? Yeah, exactly. So we always have to remember to use our kind of assumptions, right? So we're assuming that A divides BC. So since A divides BC, we know that A divides B times C times Y. Now, since A divides ACX and A divides BCY, then A divides the sum of these two things. So A divides ACX plus BCY. But now since C is equal to ACX plus BCY, we know that A divides C. So that completes the proof. So like I said, you could have done this whole thing using prime decomposition, but I think this is actually a more elegant argument than doing that. Okay, and it shows the power of this, this kind of thing.